Well, hello friends, and welcome back to the program. Now that we've done a whole bunch of exploit videos in a row, I figured it was time we start doing some mitigations. So today we're going to be implementing ASLR for user space, or address space layout randomization, because one of the issues I ran into, which trivialized exploitation a little bit, was the fact that all of the libraries in the browser process were laid out in the same exact way every time we ran the browser. So if we start the browser here and we run pmap on it, and we grep for the libraries, we can see that this here is the in order of address, all of the shared libraries that the browser uses, though, and where they're mapped into memory. So the addresses are randomized, like the base address of everything is randomized between runs, but the order of the libraries and the offsets in between them is identical. So if we start another browser, and then we do the same thing here. Oh, hold on, let me grep for lib. We can see that we have the same order with the same offsets in between them, even though this first instance started at 0254, second instance started at 2B4. So the base address is randomized to a degree, but the fact that all of these are in a predictable order at predictable offsets was extremely helpful to me when I was doing the browser exploit. So today we are going to make sure that all of these libraries are randomized in memory, so they end up in random locations in random order, and that will make exploitation more difficult, right? Because in order to get at a specific library, whether you want to get at its data or at its code, you need to know where it is. So just one step of many steps that we want to take to make exploitation harder. Anyway, so in order to randomize this, we are going to need a way to ask the kernel for a random address. So currently, the way that we wait, where is this? The way that we load these, I think, is in the dynamic loader class. Yeah, dynamic loader load program headers, which is in libelf, and it's used by the dynamic linker program. So the program that sort of helps kickstart dynamically linked binaries. So bin browser is actually dynamically linked, so it links with all of these different libraries that you saw here, right? And these are all in user lib, typical Unix stuff. And when you run bin browser, what happens is the dynamic loader will start and looks through bin browser, finds all of the libraries that it depends on, and then one by one it loads them into memory space, into the memory space of the browser process. So that loading happens here in dynamic loader load program headers, and this is where we want to change what we do. So currently we just call mmap with name and then a requested load address, and then we pass map fixed. So basically whatever address we pass into mmap here, that's the address that the library is going to get loaded at. And you can see the region name is created here. So file name : .text, which is the same thing you see here in this output, right? So like libm.so : .text. So and then a bit further down, actually, we also do the data segment. So that's the second part, both from the same file, but the text segment is rx and the data segment is rw. So read execute and read write, because you don't need to write to your text and you don't need to execute your data. That's why those are separated here. And the mapping of the data segment follows immediately after the text segment, but we actually make a private mapping for the data segment because every process gets its own unique instance of all of the data for every library, so that it can write to globals and stuff. So to make this work, we are going to need to have a way to communicate to mmap that we want a randomized address rather than a fixed address. But I guess if we're loading something that's not dynamic, but rather has a specified address, so I don't know, like a statically linked something, for example. Yeah, so if it's not a shared object that we're loading, then we still want to obey the load address request. So I think what we'll do here, first thing is, we'll split this out into, instead of like hard coding down here what flags we send, we'll say like mmap flags, text mmap flags. And then if the elf image is not dynamic, if it is dynamic, then we want to text mmap flags some new flag. Otherwise, if it's not dynamic, then we want the fixed behavior. Okay, so we'll invent a new flag and we can call it map randomized, maybe. Sort of in the same vein as fixed, right? So you pass map randomized and the kernel will just put that memory anywhere. Instead of, because I mean, technically right now it places it anywhere as well, but it just happens to be laid out one after the other in a sequential fashion. So this is more like a way to request, please actually randomize where you put this in the address space. Okay, and then we'll pass that in here. And then I guess we'll deal with the data segment later. So first we just need to actually implement mmap map randomized. So let's define that as maybe hex 100. Also need to put it in our kernel header here. Okay, and then in the mmap syscall. So map randomized is flags and map randomized. Okay, and then this really only affects the allocation of the virtual memory range, which happens here. So if map randomized is set, then we want to allocate a random range rather than a specific or sequentially bump allocated range. So this calls allocate range. I guess we can do something like this. So map randomized. So this will be sort of the old code path is here, and then the new code path, if we are I guess it's an optional range. So if we don't randomize, then we just do the old thing. But if we do randomize, then okay, so there's probably like a really nice way to do this, but I'm just gonna actually randomize an address. So get good. We need, or you know what? We should probably invent a function for this. So range is allocate or page directory range allocator allocate random randomized. and we'll say the size and the alignment. Okay. Yeah, and if that fails, then yeah, if we don't have a value in the range here, then we have to fail with enomem because we couldn't get it. And then originally I was thinking we should put all the randomization logic here in mmap, but we might as well put it in the range allocator class. Because then at least it's in one logical place, and then if we want to go and make it nicer, it's kind of easy to find. So allocate randomized, size, and alignment, let's say. Okay, so what does this do? So currently, there are two ways to invoke the range allocator. So this allocates virtual memory. It doesn't actually allocate physical memory, it just allocates a range, an available range in the virtual memory space of a program. So allocate anywhere is roughly the same as mmap null, right? And allocate specific is when you're providing an address that you would like to have to mmap, and maybe even passing map fixed. So allocate randomized will be sort of similar to allocate anywhere, except if we should just put it anywhere, literally anywhere, instead of predictably anywhere. Yeah, anyway, you know what I mean, so let's just do it. So I think if you're asking for something empty, we can just return like that. Likewise, if the size is not a multiple of the page size, then that's an issue. If the alignment is not a multiple of the page size, that's actually also an issue. I don't know why we don't assert for that here. I feel like we probably should. So I'll just go ahead and add that little thing there while we're here anyway. Oh. Kernel, assert in range allocator, allocate anywhere that alignment. Add sanity check assertion in range allocator, allocate anywhere. The alignment, the requested alignment should always be a multiple of the page size. Yeah. So I think that's just like a little sanity thing. Anyway, so let's see here. So probably we're gonna need to do this in a loop. So random address is get good random. So get a good random pointer, and then if random address is let's see. If it is if it's a kernel pointer, that we don't want that, but the kernel also has a page allocator. So I guess we should just check if the pointer is outside of the total range of this allocator, then we can reject it and try again. So if m total range contains random address, yeah, so just try again. Okay. So we'll loop here until we get a valid address that's like at least within the range of this allocator, and then we have to try to actually allocate it. So in order to do that, I guess we can just call allocate specific, right? So we call that with random address. Oh, hold on. Let's do it this way. Okay, and size. Oh, here we go. So if that succeeds, we'll just return the range. And I guess we should have sort of, I mean, if you fill up the memory space, we have to give up, right? So the address space is finite in the end, so we can try this a couple of times, but if it always fails because there's just nowhere to put it, we need to fall back to something or bail. So I think the fallback will be just allocate anywhere, which, you know, it's maybe the best we can do here. So if there's nowhere else to put it, we'll just fall back to the linear allocator. Size alignment. Yeah, and then like, I don't know, like 1,000 tries maybe. Yeah, so there's probably a better way to do this, but I don't know what that would be right now, so I'm just gonna do it this way and say, fix me. I'm sure there's a smarter way to do this. Because this should be good enough in our case right now, at least. And maybe somebody knows a smarter strategy, or we can learn something from some other system, but we have to start somewhere. So that will be that. And then, let's see. Will this just work, I'm wondering. Map randomize, wait. Oh, we're trying to compile on the host. I don't know why we're compiling the dynamic loader parts on the host. That seems kind of silly, but let's just do that. Because we compile libelf on the host to support fuzzing, but all of this stuff that's like Serenity's dynamic loader, I feel like that's not super relevant on the host anyway. But maybe we can fuzz it somehow, I don't know. Okay, so let's see what happens if we run this. Very crash. So what happens? Dynamic loader, assertion false, line 314. All right, so we have loaded, or we're in the process of loading some stuff. Like we have these elf din regions, but they will eventually go away, I think, after we've completed dynamic linking. So why are we asserting line 314? Okay, so map failed for data segment, so we're failing to map the data segment. And why is that? Let's just pair, because I'm not sure data segment. Invalid argument. Invalid argument. So wait, so what changed? So we've now mapped it at a randomized, we've mapped the text stuff at a randomized location. And then we're trying to, oh wait, I see. So the data segment is mapped like immediately following the text segment address. So like wherever the text segment gets mapped, we add to that the size of the text segment, and then we try to map the data right after. So that sort of matches what we were seeing with, like if we just disable that for a moment. So if you look at the output of pmap here, right? So we can see that that the data segment always follows the text segment for each library. So libipc.so text and then libipc.so data, and it comes like right after one another. So the address we use to map the data is simply this address plus this size. But now we are making that, random. And then that doesn't work. Interesting. So let's see why that doesn't work. Data segment address, let's say. Mapping data segment for this library at this address. Okay, let's see. Let's see what he says about that. Because I'm not sure why that would fail with invalid argument. But it's probably something silly, so we'll see what it is. Oh, I get it. Okay, so that's stupid. If we look at libgcc_s.so, so this is obviously an invalid argument because it's not page size aligned. So the randomized thing, it was not returning a multiple of the page size. Because we were just randomizing the heck out of it. Allocate specific. Yeah, so this thing actually should probably assert that what we're allocating is a multiple of the page size as well. I don't know why we didn't have that assertion. Base. Let's see, does it have any page information? Is page aligned? Perfect. Assert base is page aligned. Yeah, so this assertion will then fail because you are requesting the allocation of a VM page that's not page aligned. Looky-loo. Okay, great. So that becomes another, I think we'll do that as a separate patch as well. Range allocator, allocate specific. Wait, is this exactly what the previous commit was called? No, allocate anywhere. Requested, the specific virtual address should always be page aligned. Yeah. Okay, good. Adding assertions. I like adding assertions because that protects our future selves as well from silly mistakes. So the issue, of course, here is that we need to align the random address so that it doesn't have any garbage in the bottom 12 bits. So random address mask, page mask. Boom. Okay, we loaded. That's pretty neat. So, did it work? Let's do the browser again, because I like that. Poof. Okay, well, we can see here that looking at the addresses, they're definitely way better distributed in memory. But just for funsies, let's grep for .text maybe. Okay, so this is our text segment layout in the first instance. And oops. We'll make a second browser. And here's the second instance. And look at that. Isn't it beautiful? So now we have libc, libthread, and then browser binary, and so on. And here we have libthread, libcpp, libmarkdown. So completely different order and at completely different offsets. So that is super great. And we're spanning the range from near the bottom of the address space here to the top of the address space here, because the kernel starts at hex C0000000. So that's pretty cool. Let's see. Let's verify that something like building a program with GCC still works. Totally does. Okay, that's rad. Okay, so I think at least the kernel side of this interface is pretty good. So let's commit this. Sure. And then let's hold off on the loader for a moment because I want to look into something there. Kernel. Add map randomized flag versus map. This can be used to request random VM placement instead of the highly predictable regular mmap null footer VM allocation. It will soon be used to implement ASLR in the dynamic loader. Cool. So one thing that I don't feel quite certain about here is, I mean, it could happen, right, that we allocate space for the text segment, and then we want to allocate the data segment like right after the text segment. But what if the text segment ended up like right near the end of the address space, for example, or right next to like there's a library on his right, like right after, so there's actually no space for the data segment here. So I think the assumption here that you will always be able to fixed allocate the data segment address the way that we're doing, I think that doesn't really work. So what we want to do is we want to somehow be sure that that we're always getting like a large enough slice of virtual memory that can fit both the text and the data segments. So I think either we can no, what is the best way to do this? Maybe the easiest thing is probably to just mmap the text segment originally, but like allocate enough both for the text and the data segments, and then unmap sort of the tail of the text segment, and then fixed map the data segment in that location, because now at least we know for sure that there's nothing mapped there because we just unmapped it. So I think that's probably the easiest way. So let's just do that, and if somebody can think of a better way, then we can change it. But so that would be like text total mapping size, and that would be the text region putter required load size plus the data region putter required load size. And then we do total mapping size here. And also let's be good boys and use one of these things. And then we'll just assert that this didn't overflow. Okay. Okay, so now we'll map the whole thing in one chunk here, and then once that succeeds, then we can unmap the tail of it. So unmap text segment begin plus the data region, no, the text region putter size, requested load size, and then we want to unmap the data region putter required load size. Yeah, and then assert not reached, la la la. Arithmetic on a pointer to void. Well, I'm sorry. Would you take a U star, U8 star? Cool. Yeah. And then everything should just work, right? Because now we allocated enough VM for text plus data, and then we unmapped the tail of it, and then we remapped the tail, but this time we are mapping the data segment address. I guess we could compute this a bit earlier. Segment begin. Because that makes this here a bit more expressive if we're like unmap data segment address, right? So okay, so let's write out a comment here because this is kind of non-obvious what's going on. Let's see. We map the text and data segments in order to get allocate enough VM to hold both in sequentially in memory. Well, let's say contiguously in the address space. Then we unmap the data segment part of the above combined allocation. Finally, we remap the data segment, this time privately. And Yes. So let's see if that works. Because I think that's generally sane, and then we don't run the risk of address space collision. Yeah. So what does it look like here if you look at our file manager or something? You can see all of these beautiful random looking addresses. I really like them. That's so good. This would be so much more annoying when doing my next browser exploit, so that's a good sign. And let's commit this. So libelf implement ASLR for shared libraries, or dynamic, or shared libraries, yeah. Use map randomized, and map with the new map randomized flag to organize shared libraries, to load shared libraries at random addresses in each process. This is pretty cool. We load in order to avoid address space collisions. We we start by doing a large chunk, a map that covers enough VM for both text and data, and we unmap and remap the data segments separately. Once we know everything will work out, everything will fit. Yes, okay. So, very cool. That is very cool. So, this is not like 100% ASLR for user space, right? Because all of these other allocations here, like all of these malloc blocks, for example, they are still on consecutive addresses, but at least now we have libraries loaded at random addresses. So huge improvement in my opinion. And we will have to look at randomizing other stuff as well going forward, but today was just going to be ASLR for libraries, and now we have that, so that's really cool. Anyways, I think this will be the end of today's video, so if you made it this far, then I thank you for watching and for hanging out, and I hope you saw something interesting here. I think I like this a lot because we've been doing so much exploitation lately that it was time to switch gears and do some mitigations. So I thought it would be really interesting to take a look at sort of what the system does to prevent exploitation, or to detrivialize or complicate exploitation. And ASLR is such a good typical technique for that. So now we have started on that. Very, very cool. So yeah, thanks for hanging out, and I will see you all next time. Bye.